Okay, recording. Share screen. Okay. Okay, now the next thing we want to consider a more systematically exploring examples of subspaces. Okay, so here's the first kind. Let's recall. Maybe let's not do that. Let's recall the following definition. Suppose you have vectors v1 through vr, say, a1 through ar are just numbers. The expression a1 v1 plus a2 v2 plus ar vr, which by construction sits inside Rn, is a linear combination of the vectors v1 through vr with coefficients being these a's, a1, a2 through ar. Okay, this is just a notion. That is, if you have numbers and you have vectors and you form this expression, what you get is called a linear combination. Okay. Now, we can consider the following set definition. Again, you have, let's say we have vectors v1 through vr in Rn. We define the notion of what's called the span of v1 through vr is the subset, the following subset. First of all, it's denoted by SP, v1 through vr. It's the subset of all linear combinations of these v's. I.e., this is the subset of all linear combinations vectors v1 through vr. Okay. Now, one easy fact about a span is that you get a subspace. Evidently, it's a subset. Okay. Okay. So proof. As you may still remember, to check that we have a subspace, we need to check three properties. First one is called S1. That is, we need a zero vector. Now, zero vector is sorry. Let's do it this way. right? In other words, we need the zero vector to be in the span, so we need the zero vector to be a linear combination of these vectors. So this is an R. Okay, so we need to write somehow the zero vector as a linear combination of the V1s through VRs. That is, we need to choose some numbers A1 through AN for them. Now the choice we make is to take all these A's to be 0. Okay. By definition, this is a linear combination, therefore it belongs to the span. On the other hand, if you just look at the construction, right? And 0 times a vector gives you the 0 vector. So all you have here is a sum of 0 vectors. That is the 0 vector. So therefore, the 0 vector is in the span. Okay. Now for S2, you have 2 vectors to begin with. Let's call them Y and Z. Both linear combinations of the V's. Okay, and for S2 to hold, we need Y plus Z to be in the span, which means we need Y plus Z to be a linear combination of the V's. Need Y plus Z linear combination of the V's. And what else can you do at this point? You can, you just compute what Y plus Z is. And at this point, the natural thing to do is to collect terms that are proportional to the same vector. So A1V1 and B1V1 should be put together. A2, I don't know what happened. A2V2 and B2V2 should be put together. ARVR and BRVR should be put together. If you do that, you get this. Now you can further processing this using one of the properties of scalar multiplications to write A1V1 plus B1V1 as A1 plus B1 times V1. A2V2 plus B2V2 can be written as A2 plus B2 times V2. And likewise, now this is a linear combination of the V's. So you indeed get Y plus Z to belong to the span. Okay. Now, the last thing to check would be the property S3. For this, you need a vector in the span. And you also need a number. called C. And then you want to consider C times Y. And you want C times Y to be in the span. So you need C times Y to be a linear combination of the V's. Okay, C times Y by construction is C times this. And now again, you have properties of scalar multiplication that allows you to distribute these multiplication by C into each term. So C A1 V1, C A2 V2, C AR VR. And again, there's another property of scalar multiplication that allows you to combine two scalars multiplied together first before multiplying it to the vector. So you get CA1 times V1, CA2 times V2, and so on. And now this evidently is a linear combination of the V's. Okay, so this shows that the scalar multiple of Y is indeed a linear combination, so still in the span. Therefore, S3 holds true. So, therefore, the subset span here is a subspace. Okay, let's see some examples. If you just have say a single vector, this is for example a vector in R3. Span of this single vector would be just multiples of this vector, right? Because there's no addition possible here with a single vector. All you can do is multiply by scalar. Right, so say this is our V. Then the scalar multiple would just probe this direction and this opposite direction. You know, because this is scalar multiple for arbitrary real number, you get to probe both directions at all the possible distance or possible lenses. So the span of these single vector V just traces through a line. So now let's consider two vectors. In fact, we can do Rn, not just R3, right? In fact, this is the previous discussion does not need anything specific about R3. You just need a single, you just need a vector. Now suppose I have two vectors in Rn. I can consider the span of these two vectors. As the theorem says, this is also a subspace. As we've seen before, if you are to add two vectors, you'll be forming this parallelogram. But now what you're doing is you're adding various different multiples of u and v. So that will allow you to go to all sorts of directions. In fact, the span of u and v is the whole plan here. Okay. Okay. Now let's see here. Now the next class of examples is the following. So suppose, A is an m by m matrix. Okay, and B is a m by 1, well, vector, m-dimensional vector. I guess I don't need to use that right now. So let's just look at A. Okay. And we can make the following definition. The null space also known as kernel of A is defined to be the following subset. First of all, the notation is n of A. It consists of all vectors, n-dimensional vectors, such that A times x is 0. Okay. By definition, this is a subset of Rn. The requirement for being in this subset is that A times x is 0. Okay, so clearly it's a subset. Now the observation that we can make is that n of A, the null space, or kernel null space is a subspace of Rn. And the proof is also very simple. Again, by the previous theorem, we checked the 3 properties required. The first one is to say that the 0 vector is in n of A. And that's just because A times the 0 vector is always the 0 vector, right? That's that. There's nothing interesting here. Now, for S2, we need to check that if you have U and V both in n of A, then we want U plus V to be in n of A. Now, to begin with, if U and V are both in n of A, that means AU is 0, AV is also 0. Then we want U plus V to be in n of A. To see this, we have to consider A times U plus V, right? And we need it to be equal to 0 in order for U plus V to be in n of A. But according to one property of matrix multiplication, A times U plus V is AU plus AV, which is 0 plus 0, because U and V being N of A, AU is 0 and AV is 0. So we have 0 plus 0, therefore 0. And that's why U plus V belongs to N of A. Now the final property S3 is about multiplication. So if you have U in N of A and C a scalar in R, and what this means, again, being in N of A means that AU is 0. What we want is that C times U to be in N of A. Now to see this, we consider A times CU. Oh, well, and we need this to equal to 0, right? But that's not hard to see because A times CU, according to another property of matrix multiplication, is C times AU, which is C times 0, which is 0. Again, here we've used that AU is 0. Okay, so that's property S3. Okay. Now note. So now that the theorem is proved, we should interpret this in the way that we did in chapter 1, right? So given A, we have the homogeneous system AX equals to 0, right? The subspace, the null space of A is the space of all solutions to this system. AX equal to 0. That's just the definition, but it's nice to keep in mind that N of A can also be interpreted as the space of solutions. This makes contact with what we've done in the previous chapter. Okay, and now let's look at some example. Say A is, well, you can really just consider various different kinds of examples. Say, for example, you have this 3x4 matrix called A, and we want to describe N of A. Because N of A is the space of all solutions, right? What this means, when you ask to describe N of A, you're asked to describe all the solutions of the system AX equal to 0. Namely, you just asked to solve the system. To describe N of A is the same as solving the system. equals to 0. And we've done that before. We certainly know how to do that. So start with an A. And I'm gonna skip the lengthy part of this discussion, namely after several different row operations, we bring the matrix into reduced row echelon form. Which in this case is the following. Sorry. We should begin with the augmented matrix. That's if we are to solve a system, we should begin with the augmented matrix. Augmented matrix. All right. So now what? Now we proceed according to the way we solve systems. Right, the variables corresponding to the leading ones are the dependent variables. In this case, x1 and x2. Now the two equations that remain are the following. Okay. From this, we solve for x1 and x2. X1 is minus x3, sorry, minus 2x3 minus 3x4. X2 is minus x3 plus 2x4. And now for the purpose of describing n of A, we need to write everything in the matrix, sort of vector form. Vector form solutions. We've seen how to do this before. Okay, so we have x1, x2, x3, x4, and they are minus 2x3 minus 3x4 minus x3 plus 2x4 x3 x4, and we're going to break these into two terms, one term proportional to x3, the other proportional to x4. Okay, and that gives us minus 2x3 minus x3 x3 0 plus minus 3x4 2x4 0 x4, and then we can factor out x3 and x4 respectively. Okay, so this is therefore the vector form of solutions to the system, the homogeneous system Ax equals to 0, and this therefore are the vectors belonging to n of A. So n of A is therefore therefore has the following description. No. Of A looks like now let's call it x3 minus 2 minus 1, 1, 0, x4 minus 3, 2, 0, 1, x3, x3 and x4 are real numbers. And by the way, you recognize that this is the span of the two vectors written here. Okay. All right, so that's one example. Now, consider another example. Let's say W is in R3 is a plane passing through the origin in R3. Now I want to argue that in fact this W is a null space and hence a subspace. Now in general, if you have a plane passing through the origin, its equation takes the following form: ax1 plus bx2 plus cx3 equaling 0. Okay. Now if you rewrite this as a matrix product, you get this. ABC here, this is a 1×3 matrix times the column vector or 3×1 matrix x1, x2, x3. Okay, so now if I take these 1×3 matrix to be my A, we get that W is equal to n of this A. And hence is a subspace. Okay. That's another example of the null space. Now, we're given n by, again, we're given an n by n matrix. There are something else that we can associate to it. It's called the range. The range of A is defined to be the following. First of all, the notation is R of A. It consists of vectors Y, Rn, no, vectors in Rm. Okay, so that Y is of the form Y equals to A times X for some X in Rn. Okay, so by definition, this is a subset of Rm, and Yes. These are, in other words, the range of A is the vectors in Rm of the form Ax with various possible x. Okay. Now, let's see here. Theorem. You expect, of course, that the theorem is going to say that the range of A is a subspace of R of M. Now the proof, well, you can do this in some different ways. You can certainly check as the properties S1 through S3 as we did before in other situation. But you can also do the following. Let's write A in the following form. In column form, let's say. Namely, I can describe A by listing its columns. There are n of them. Then what? And let's also write X to be the column vector x1, x2 down to xn. Then Ax is written as x1a1, x2a2, xn an. Okay. Now, to say that y in Rm is of the form y equals to Ax is the same as saying that y is equal to x1a1 plus x2a2 plus xn an, which is a linear combination of a1 through an, and we have a name for this. It's in the span of the a's. So what this means is that the range space, or the range of A, is simply the span of A1 through AN. And this is a subspace as we've checked already. Okay. Now there's one more thing to remark, that this subspace here, how you form this subspace, you have your matrix A, and you pick the columns, and you take the columns A1 through AN, and you form the span of the columns. So such a subspace has another name, is called the column space of the matrix A. Okay. Now, now let's consider an example. So suppose I have this A, a 3 by 4 matrix, 1, 2, 1, 1, 1, 2, 3, 5, 4, 1, 4, minus 1. And of course, we've seen it already in this example right here. there's a good reason for that, which we'll come to in a minute. Okay, so now the question here is to describe this range, the range of this matrix. That means describing all vectors in R3 of the form B equals to AX. Okay. Okay. All right. Let's do that, and let's think about this. Think about how we're going to do this. We've seen this, we've certainly seen this equation before, Ax equals to B, but we viewed this as saying that it's an equation with A and B given and X being unknown. We know how to deal with that. But the point of view now is this. We are trying to find the B's so that Ax equals to B has a solution, right? So for this, we need to find all B for which Ax equals to B has a solution. Okay, and that we can now we know how to do, right? Because now this is an old problem. We have assistant Ax equals to B, and we're trying to solve it. We can certainly decide if it has a solution or not by running the row operations. So again, let's form the augmented matrix like these, and let's take some time. It's going to take some time, but you will be able to find the correct row operations and turn the augmented matrix into reduced row echelon form, which will be the following. Okay, and now right here you have okay, so what is this? This is, as you can see, in reduced row echelon form. But now keep in mind the question is, or the question is whether this system has a solution or not. And we know how to decide on that, right? The reduced row, we have to look at the reduced row echelon form. And if it has a row that's all zero except one entry being one, sorry, if you have a row in the reduced echelon form which has all the entries zero except the last one, then that system has no solution. Otherwise, it does. Okay. So in this case, the problematic or the possibly problematic row is this last one, where all the entries here on the left side are zero, and this last one here and this last entry here can be a problem if it's not zero. So the system X equals to B has a solution if and only if this last entry minus 3 b1 plus b2 plus b3 is equal to 0. Right? If it's a 0, if that's 0, then you have a 0 row and that's no problem. If it's not 0, then you can turn it into a 1 and you get an inconsistent equation. Okay. Okay, so now we can proceed to describe the range of A. The range of A is then all the vectors B, B1, B2, B3, such that minus 3B1 plus B2 plus B3 is equal to 0. And you can certainly rewrite this as follows. B1, B2. Okay, if we have fixed B1 and B2, then B3 is determined by this. It's 3B1 minus B2. And B1 and B2 are arbitrary. Okay. And furthermore, you can rewrite this expression by splitting into two terms, one term proportional to B1 and the other proportional to B2. Just like what we did before. Like that. And finally, you can factor out B1 and B2. Okay, and get this description of the range of A, and guess what? It just happens that this example is yet another example of the span of a matrix, the span of two vectors. Okay. So now let's this seems to be a good place to stop. So we'll stop here, and there's another example of subspaces I will consider next time.